It's not yet in the presentation mode, but
yeah, you can make it full screen if you want. That's all right, Punesh. I think, yeah. Right. Okay, I think people are coming in still, but let's start on time. Great, welcome everybody. So we have a special colloquium today. It's special because, of course, the special nature of the speaker and the topic. Bhuvanesh Jain is very special to us, but also it's because it's on a different day from our regular colloquium and a different time. And I'm glad that people have actually turned up at a different time slot on a different day of the week. Thank you very much. And we have to make these adjustments in time in order to accommodate people in unusual time zones like the North American time zone, even though it seems Bhuvanesh has woken up pretty early. Bhuvanesh Jain is no stranger to Ayuka. He's been here many times. In fact, well, I can remember a recent visit where he gave a fantastic talk. Today, he's talking about the early results of the dark energy from the dark energy survey. I've known Bhuvanesh Jain from his time when he was a PhD student at MIT. He did his PhD at MIT, then moved on to postdoctoral fellowships at Johns Hopkins, and then but before that to the Max Planck Institute in Germany. And then he's been at the University of Pennsylvania for almost 20 years now, my goodness. And he now is there, the co-director of the Center for Particle Cosmology, and a very well-known figure in cosmology. Today, we are very, very curious to look at the early cosmological results from the Dark Energy Survey, in which he's played a very important role. He's chair of the working group on lensing at DES. So over to you, Bhuvanesh.
Thank you very much, Shamak. And thank you, Sarhad and Kandu, for organizing the talk. It's really nice to see you, even though over Zoom. So I'm going to talk about the Dark Energy Survey and summarize the status of cosmology as I understand it. So we completed our survey a couple of years ago and have only analyzed half the data. So it's a 6-year survey. So this is called the DES Year 6 results. It was a lot of work. As I'll show you, there's 30 papers that have been completed over the last several months that capture all of this work. So naturally, I will give you only some snapshots. So I'll talk about how we measure cosmic expansion and the growth of structure with galaxy surveys. I'll show you DES's results. Then I'll talk about this comparison of galaxy surveys and the CMB, called the late universe versus early universe tension, and talk about what lies ahead. So what makes the universe expand? Just a few slides of introduction to cosmology. What does expansion mean? It means that the separation between any two objects grows, like the scale factor, which we call A of t. And the expansion rate, h of t, is defined as a dot over a. Its value today is h naught. Towards the end of the talk, I'll circle back to one of the puzzles in cosmology, that the universe today seems to be expanding faster than our cosmological model would predict. So what determines this expansion? The constituents, matter and energy, and we believe there's something called dark energy, which is making the universe accelerate. So these are the equations for the first and second derivatives of the expansion scale factor that show you how the energy densities of matter, dark energy, and radiation determine the expansion rate, and how the energy density and pressure set the acceleration. So I won't talk any more than to note that we have what we call a standard model of cosmology, which is lambda, the simplest form of dark energy, cold dark matter, which is something else that we've not yet established, but it's a kind of a description of how dark matter behaves, and general relativity, which I'll abbreviate as the lambda CDM model. One generalization which we'll test is if it's not lambda, but rather it's dark energy with some equation of state W, then we will treat W as a free parameter and test if it's consistent with the lambda CDM value of -1. So that was the expansion. The growth of structure at linear order is given by an equation like this, where delta is the density fluctuation. So delta itself depends on the expansion rate, because the faster the universe expands, the slower things grow due to this Hubble drag type term. What do we measure? We measure two-point correlation functions of fluctuation variables. The two that I'll be talking about is the galaxy density, the number density fluctuations of galaxies, in particular in 2D on the sky, and the lensing shear, which is a complex quantity that determines how a galaxy is stretched. So I'll be talking about the two-point autocorrelation of the galaxy density, the two-point autocorrelation of the lensing shear, and their cross-correlation. This we call the 3x2 point data vector. How do we use it to test models? Well, the standard model has 6 to 7 parameters: the densities of dark matter, baryons, dark energy, neutrinos, the power spectrum of fluctuations, namely its amplitude, which we'll call sigma 8 or S8, and its slope, and the expansion rate H. We use Bayesian statistics and MCMC sampling of a parameter space that has these 6-7 parameters and up to 20 other parameters that are called nuisance parameters, but they include all kinds of physics and measurement systematics that we have to fit for. And then we figure out, is the standard model a good fit? Is some alternative model an equally good or better fit? And whichever, if it's a good fit, then what are the values of the parameters? Okay, sorry for the super quick intro, but I wanted to save some time for the results. So let me introduce the dark energy survey. This is our telescope, where I spent a few wonderful nights doing shifts observing. It's the Blanco telescope, a really old 4-meter telescope, but it works pretty well. And we had the DES collaboration, in particular, the team at Fermilab built a big camera with a 3-square-degree field of view that let us carry out the survey. So this is a picture of a known cluster, one of the earliest cluster images we took. You can see it's a ground-based picture, so it doesn't have the exquisite sharpness of Hubble, for example. But as you'll see, we can cover a wide field of view. So this is one snapshot in different filters combined to get a color image of the DES camera. So this, for reference, is the size of the moon. So you can see our area is significantly larger. So we take like a bunch of 2-minute exposures in different filters and try to tile the sky. So this is the footprint of our camera. And this is, say 1 night's observing. And then over 6 years, we take 10 to 20 exposures per filter over the 5 filters and create the survey of the southern sky. It's 5,000 square degrees, so that's a bit over a tenth of the sky. The footprint was chosen to overlap with a CMB survey, the SPT survey. So this is the largest cosmological galaxy survey with this 540 megapixel camera. We have images of 200 million galaxies. Well, there's more, but these are the galaxies that we can use, their positions and their shapes, through which we measure the gravitational potential via lensing. There's also a time domain survey. For cosmology, it's supernovae that are used, but we also have major discoveries of in the outer solar system, dwarf galaxies in the Milky Way, and all kinds of other signs. We have two wonderful peer surveys, the KID survey and the Subaru HSC survey. You've hopefully heard a bunch about the Subaru HSC survey from Sirhud. These are also extremely powerful surveys, and we really enjoy discussing and comparing results with our friends in these surveys. This is, I guess, Hendrik Hillebrand's all these kind of summary tables are necessarily incomplete, but just to give you one glimpse of the strengths of the different surveys, ours is mainly just like the size. We have a big field of view and a bunch of time, so we could cover 5,000 square degrees. HSC has the best instrument, great seeing, and deep imaging. So the depth is probably the biggest advantage. The KID survey has huge wavelength coverage. So they have infrared coverage over some part of their footprint. I'll show just a couple of results from these surveys as well. So this is the team of people who were, the DS collaboration itself is, I think, about 300 people. These are the 40 or 50 people who were involved in these 30 papers. Of course, I can't talk about all of them, but the students and postdocs at Penn who worked with me are in bold here. Me and my colleague, Gary Bernstein. So Cyril Dude, Carla Sanchez, Marco Gotti, Marco Roveri, and Lucas Secco and Shivam Pandey were my students who led important parts of the analysis, and Minsu, Tay, and Jason have worked on other aspects. It's also been fun working with undergrad students, but their work is more on clusters and other things. And some of these colleagues made plots and slides that I borrowed. Okay, so before we show actual measurements, just 2 minutes on lensing. So as many of you know, if these are the images of unlensed galaxies, then a big galaxy cluster would distort them, coherently shear them into a pattern that looks like this. This is, 10 or tens of percent. In a typical line of sight, you see a 1% distortion, when the correlations that we measure are typically at the 0.1%. Okay, so when I say that we measure the amplitude of fluctuations to 2 or 3% at the end of the day, the measurement feat that's involved is a 2 or 3% accuracy of a 0.1% distortion. So needless to say, that's challenging, especially given that this is what a raw image looks like. Many of you who've observed will not be surprised at all these artifacts of satellites and cosmic rays and electronics that are present in these images. Those of you who are theorists should, quit cosmology right now, because the idea that we can measure these shapes, because the galaxies that we typically work with are the ones that you barely see, the little smudges that have, maybe not even 100 pixels. And the idea is that an individual shape can have like a 10% level noise on it, uncertainty in its, if it ellipses basically, but that when you average over these 200, actually in this results 100 million galaxies, so that's 100 million squared pairs of galaxies, then in that averaging, the residual bias is much lower. Let me pause here in case there are any questions. Sorry, I meant to do that earlier. Okay, please feel free to interrupt. A few questions during the talk are great. Okay, so from that image, I'm not going to quiz you on these many steps and their different dependencies, but to give you a flavor for what is involved in going from those images to cosmological results, these are the categories of data analyses. There's redshift estimation in blue, where we basically use the colors of galaxies to get redshift distributions. There's shape measurement over here, where you take these pixelized images of each galaxy and estimates its ellipticity. Then using the positions, we measure clustering. We require simulations to generate many mock surveys that we use to test our code and analysis methods. The analysis methods themselves involve a bunch of theory and covariance estimation, and then we get our results. So this is one kind of bottom line result. Using the shapes of those 100 million galaxies, we've generated a mass map. This is using lensing to reconstruct the projected mass distribution on the sky. So there's one mass map from the Planck satellite that covers the whole sky. That is the entire mass distribution projected to redshift 1100. This is the mass distribution using our galaxies as background wallpaper. So it's up to redshift 1 typically. But as I'll show, we also bin the galaxies in different redshift bins, so we get the projected mass at different distances from us. So this map is in a paper led by Neil Jeffrey and Marco Gatti. Okay, so I'll go through the few steps that we take to make the measurement. First, let me introduce our galaxies. We have 3 samples. 2 are bright galaxies that we use as lenses. So these are foreground galaxies, if you like. And there's 3 million in one sample, 11 million in another. A full 100 million galaxies are the background galaxies used for the lensing measurement, and they're called the meta-calibration sample. These words have, I'm not going to explain the origins, but the 2 lens samples are called red magic and maglim, and meta-calibration is the shear estimation methodology, which is why the background sample is sometimes called meta-calibration. So to get the redshift distributions, we use different methods that I'll mention briefly next, but this is the result. So this is redshift 0 to 1.6. The lens samples have, fairly tight redshift distributions. We didn't want more than 5 bins for analysis complexity reasons, but these redshifts are certainly estimated better than that. For red magic, 0.02, 0.03, a scatter, and maglim a little, twice that. So these are 5 lens bins for the red magic and maglim samples. You can see they extend to a bit beyond 0.1. The sources, we made some significant, we think, advances in estimating the redshifts, but the distributions don't look pretty. We just think we understand the biases, possible bias in them to a very tight level. So the mean and width of these distributions is very well estimated. But you can see the sources extend, they go as low as the lenses and higher. So these are the 4 tomographic bins we use for lensing tomography. Okay, I'm taking a little time on the slide because these are the basic ideas. So on the sky, every galaxy, has some image and a position, but we use the redshifts to separate them in distance along the line of sight. And we have these lens galaxies denoted by crosses, source galaxies denoted by ellipses, and we measure the autocorrelation of galaxy positions, that's the clustering, cross correlation with lensing, and autocorrelation of the lensing shapes. The last one is called cosmic shear. There's two of them actually, because the shear is a complex number. The second one is called galaxy-galaxy lensing. It's the tangential shear around a lens galaxy. And the galaxy clustering is called W theta, since the days of Jim Peebles. And we're not about to mess with what Peebles and co called it. So this is the subject of an interesting technical talk by itself that you can invite any of these lead authors to give. But how do we estimate redshifts? We did a kind of fancier machine learning-y extension of the traditional method of using galaxy colors to do it. That's called SOM-PZ redshifts. Completely independently, we use spectroscopic subsamples available from various other means to use a trick where you cross-correlate our galaxies with unknown redshifts with galaxies with known redshifts and estimate the redshift distribution. There's a third method that we use to supplement information, and that's the trick that there's a whole bunch of scales, small scales, where the clustering is nonlinear and we don't want to model it. We don't use them for cosmology, but we can still use the ratio of the lensing signal, which depends just on the redshifts and distances, to constrain the redshift. So that's called shear ratio. So long ago, I had written a paper on dark energy with this statistic. It turned out that was pretty optimistic because it's much more sensitive to, it's a much more robust estimate actually of distances than it is sensitive to cosmology. So it came to some use. So now I'll introduce our three two-point functions. The first is galaxy clustering, and we measure it with these two samples. And galaxy clustering is affected by all kinds of stuff, namely extinction due to dust, atmospheric issues, dust in the galaxies themselves, in addition to dust in our galaxy, air mass, position on the sky, position with respect to galactic latitude, and so on. So I'm going to give you a little preview of a problem we found. And the problem is related possibly to the difficulty of estimating galaxy clustering. Galaxy clustering is pretty much the first thing that was measured in cosmology. So it's both easy and really hard to get exactly right, because any source of fluctuations in the galaxy density just add to the signal. And we are slowly learning that because it's a simple scalar quantity, it's pretty hard to correct for these additive errors. The lensing shear has a vector quality, because it's a complex number. So that lets you, average out many systematics, or at least test for them. Because, galactic dust doesn't know which way the shear should be oriented. But anyway, for W theta, this is theta times W theta, because W theta is falling with angle. So if you want to look at it more closely, you multiply the y-axis with theta. The gray bands is the data we don't use because it's on small scales. So, this is roughly 5 megaparsecs is the boundary here. So the points that are in the white region are the points we use. This is the first redshift bin, second, third, fourth, fifth, sixth for the maglim sample. There's 5 bins for the red magic sample. And the raw measurements are the faint red points. I hope you can see them. Then we make these things called survey property maps. So for everything that we can think of, like air mass, we make a map. We come up with some weighting scheme for how it might affect the 1-point galaxy density. We correct for it, and we end up with the green measurements. And the main point I want to make from this slide is that you can see the correction is pretty big for especially for some bins. And you know, it has to be good to 2%, and you can see it's like a 20–30% correction quite often. So I'll return to this measurement in a few slides. This is galaxy-galaxy lensing. So it's the tangential shear around a foreground galaxy using sources at different redshifts. So these are the 4 source bins. These are the 6 lens bins. And sorry, I might as well mention that these last 2 bins we didn't end up using. That's why they're fully grayed out. So already you can see one thing, that the best fit model fits the data pretty well. If you stare at it long enough, you find some things that you might worry about, like this is systematically high, that you might see a few points going up and down, but every test we do for you know, chi-square type tests, the model fits the data pretty well. This is the lensing autocorrelation, shear-shear correlation. This was believed to be the hardest thing to do from galaxy surveys, but we think we are quite satisfied with our measurement and the tests. So I won't have time to explain, but you know, you have an ellipticity, so you can think of 2 vectors that you dot product, and you can construct 2 2-point functions out of it. They're called xi plus and xi minus. Again, the shaded region is data we don't use. The light shaded region that is data that we decided we actually could use. So I'll show you both results. Again, you can see that the model fits the data quite well. You can see the error bars are at the 10%, 20% level per bin. And when you combine everything, signal to noise is 40. So 2.5% measurement of the amplitude is possible just from lensing. So this is an improvement over our previous results of the year 1 analysis in signal to noise. How it translates to parameter constraints depends on the methodology. So we'll see that too. And there are many panels because with 4 bins and auto and cross correlations, you get all these combinations. You know, because the lensing matter that's lensing 2 different bins lenses both of them, there's additional information, cosmological information in all the cross correlations too. So that's different from galaxy angular clustering, where only the autocorrelations have cosmology, more or less. Any questions while I take a sip of coffee?
Maybe we can do the questions at the end.
Sure.
Right, yeah.
I'm pausing just for a break as well.
Well, if somebody has any questions at this stage, they can raise their hand, and we can see the raise hand option. Bhunesh, of course, is a very well-loved teacher for this reason. He knows where to pause and ask for questions from us. Okay, nobody's raised their hand yet.
I'll keep going.
Yeah, go ahead.
So this is a full data vectors, we call it. This is the lensing two-point function, galaxy clustering, sorry, here galaxy clustering and galaxy-galaxy lensing. And you can stare at one thing very quickly. The lower panels show the residuals from our best fit model. So, of course, neighboring bins have some correlation, but if you go like 3 or 4 bins away, you're starting to get uncorrelated. So you can ask, are there any anomalies? That's an exercise we do, as rigorously as possible. But the first thing that we all do, of course, is to just look at the plots. So here's one so I'm not going to show you, of course, the hundreds of tests we did, but I will show you a few. So this is a test of the analysis machinery using simulations. So first we generate a synthetic data vector, just like the same theoretical tools we use to fit the model. We generate a data vector. We use the covariance that we've estimated, and we carry out a mock analysis. That's the black lines. These are the 2 parameters, S8, the amplitude of fluctuations for lensing, and omega matter. The blue is quite a non-trivial test. The blue is done by generating a fake survey or many fake surveys and injecting all the systematics that we can inject into it, and then doing the analysis. So we think that at least the systematics that we've thought about, we know how to mitigate. Here's another plot. A lot of work went into this, and Shivam Pandey, my graduate student, played a big role, along with Elizabeth Krauss and Xiao Fang in this analysis, and Joe DeRose in the simulations. So we came up with a threshold. There's a set of systematics, photo Z systematic, intrinsic alignments, baryons, that we think could show up in our error budget. There's like always a few dozen, but there's only 2 or 3 or 4 that are real worries. So we set a threshold that the contribution of these leading systematics should be below 0.3 sigma, where sigma is the statistical uncertainty. So this is a test where we generate a data vector using a hydrodynamical simulation that has baryons. We don't treat baryons. We try to just exclude the effects of gas physics through scale cuts. And when we do this end-to-end analysis, we find, this is one of the worst cases, a 0.2 sigma shift due to the unmodeled baryons. So that's our tolerance. And we learned many things about the perils of high dimension parameter spaces. So as you increase model complexity, you are susceptible to all kinds of projection effects and biases that can arise due to the interplay of priors, non-Gaussianities, and projection effects. This is one slide on another huge effort, which is the estimation of covariances. You can treat this figure as just kind of an impressionistic art, because it's going to be half an hour just to explain this figure. But this is our attempt to take into account the uncertainties and the cross correlations between different bins and different observables. And this thing on the right shows you all the higher order and subtle effects that we tested for. For example, curved sky, the limber approximation, the effect of redshift space distortions that creeps in the bins, non-Poisson shot noise, and so on. So you can see this is the effect on the covariance, and it's pretty well controlled. We have built up the machinery to handle a more complicated survey than ours, in particular non-Gaussian terms, that'll be relevant for the LSST survey and the Euclid surveys, which are starting in a couple of years. So the bottom line of our model is we have the 7 cosmological parameters, 9 parameters for our astrophysical model, mainly galaxy bias and intrinsic alignments, and 16 calibration systematics like shear calibration and photo Z calibration. And this is showing for intrinsic alignments how they contribute to the signal relative to lensing. So intrinsic alignments is the fact that 2 galaxies that live nearby tidally affect each other, or they're both affected by the large-scale tidal field. Whereas in lensing, we are only interested in how their shapes are sheared by the matter between us and them. So we need to also fit for their intrinsic alignment, which we do. Okay, so I'm going to show you a series of these contour plots. So S8, sorry, I should have had an equation, is sigma 8, the amplitude of mass fluctuations, times omega matter to the 0.5. It's kind of an effective amplitude of lensing fluctuations parameter. You know, one thing we've learned is that even something simple like the amplitude of mass fluctuations is not a uniquely defined quantity. If you measure, say, of course, we can't see the dark matter, but if you measure, say, the galaxy number fluctuations, then in the linear bias approximation, you're measuring the mass fluctuations. If you measure lensing, you're measuring fluctuations in derivatives of the projected gravitational potential, which is a perfectly respectable thing, but it's different from mass fluctuations because potentials depend on the mean mass density itself. So S8 mixes the amplitude of mass fluctuation sigma 8 and omega matter. So that's the parameter we use to compare with the CMB. So this is our measurement. And you can see the uncertainty is a bit under 3%. This is a measurement of omega matter, which is 10%, so much weaker than the CMB. But CMB measures it at high redshift. We are measuring it at low redshift. And if you look at WCDM, so these numbers are for lambda CDM. Then for WCDM, we get W is very close to -1. The error bars are not extraordinarily tight, but we are certainly consistent with lambda CDM. These are the 2 subsets of our data vector. So cosmic shear in blue, which is pure lensing, constrains these parameters by itself. Galaxy clustering and galaxy-galaxy lensing in orange need to be combined so that you can fit both for galaxy bias and for the amplitude of mass fluctuations. So you can see we get a consistent result, but I'll tell you the puzzle that we had to deal with to get to this point in a second. And when we combine them, we get these black contours, which is a final result. So that's the story. What more do we have to say about it? So we can compare to Planck. So this is where these cosmic tensions come in. So we find that indeed, our estimate of amplitude of fluctuations is lower than the CMB. So it's lower than what we measured from the CMB, and then time translate to the present using lambda CDM. The difference is not huge. So we had a p-value of 0.01 as our threshold, and we're well above that. So we formally say we are consistent with Planck. In fact, this is just lensing. If we use the full 3x2, this is 2 sigma. The black is more like 1 sigma. This is a more detailed look at the cosmic shear result. So this is Planck. This is the measurement I just showed you. Now we're marginalized down to this one parameter. If we do more aggressive scale cuts, which we think is quite reliable, then we get this measurement. Error bars are smaller, but the central value shifts a bit. So the bottom line is there's a 2.3-ish sigma difference between us and the CMB. You might ask, well, how robust is this? So then you can look at all of these tests that we do, changing the redshift measurement, using small scales, how we treat blending of galaxies, and so on. If we just neglect observational systematics, you get a greater tension, but of course we don't recommend that. If you use large scales only, you shift that way. So you might say, well, maybe there's some problem in the nonlinear modeling. We don't think so, but you can decide for yourself. You know, one caveat is that people often quote tensions in this S8 parameter, but the compatibility of these two data sets must be examined in the full parameter space. And there, the tension metric that you might end up with is a little different. Something that a major advance that we made is we did nonlinear bias modeling. This is work led by Shivam Pandey again, where he has a methodology paper that we think is a very comprehensive study. Because surprisingly, people have done a lot of work for bias modeling for redshift surveys, but for where you have to take into account RSD, redshift space distortions. But for imaging surveys, developing it fully and just practically implementing it using a fast enough code that you can do MCMC estimation. We think this paper does that job pretty adequately for present purposes, and we're still working on advancing it. So this is called the one loop perturbation theory model. We add, 4 new parameters, but we fix, sorry, 3 new parameters, but we fix, right. We introduce 4 new parameters, we fix 1 to 0, and we fix 2 to what's called the coevolution value. And we do a lot of testing to show that. So at the end of the day, we are left with just one free parameter describing nonlinearity, B2, that we fit for. And we run into this, mild frustration that we have this complex model we can push to smaller scales, 4 megaparsecs instead of 8. But the gain in cosmology is real, but not enormous. So this is something we are finding more and more in cosmology, that as the data is getting really large and statistical errors are getting really small, the modeling uncertainties and systematics eat up a lot of information. So you end up with very robust results, but the gains come harder. I'll skip over this, 2 tests, 2 different alignment models. Okay, so I want to spend a few minutes telling you about a problem we found, and we have not yet resolved it. We found that galaxy clustering doesn't fit the other part of the data set. So this is one way to show it. The red points are the measurements of galaxy clustering. The blue is what we predict if we used the mainly lensing part of the data set. And you see that there's a few bins where the measurement is 2 or more sigma higher. This is a more dramatic illustration. So this plot shows in orange, I'll just jump to this. If we used what we thought was a better sample, and we use this 2 by 2, the galaxy clustering and galaxy lensing part of the data set, then we can estimate S8 and omega matter, and we get quite a different result from our baseline result shown in black here. I won't explain all the other curves. Okay, so we have a 2 sigma internal inconsistency. So after unblinding, we spent 6 months testing and agonizing over this. And we made a decision to swap a galaxy sample. Luckily, we had prepared 2 samples. And because this one was inconsistent in more ways than one, as I'll show, we used the other sample for our fiducial analysis. And that sample shows results that are completely consistent with lensing. So in fact, even when we use this, when we add in lensing, we get the dotted, sorry, I can't see this. We get the dashed curve, which is quite consistent with our final result. But we were worried enough by this subset. So you might have heard of this thing called galaxy stochasticity. We don't use that term because we think that we found some difference between galaxy clustering and matter clustering or galaxy-galaxy lensing that's not due to true stochasticity, but it's due to a systematic. So this parameter Xlens is the ratio of the bias estimated using galaxy-galaxy lensing and galaxy clustering at fixed cosmology. So they should give the same answer, but you see in the blue points, we get something consistently below 1. So this is a parameter that we introduce, and we call it, a measure of systematics. So even for the sample that we did use, the black, we found this parameter to be below 1 for 2 bins that we then discarded. Sorry, I didn't explain this very well because it's a very complicated story that I'm happy to discuss. But as I mentioned to Serhad, hopefully in a couple of months, we will have some real insights and resolution. And you can have, one of the people leading this analysis, Shivam Pandey, to come and discuss it because it's very fascinating. And it's also really relevant for LSST and other surveys, which are planning to use very similar samples to these. Okay, so that's everything I wanted to say about DES. You can look at any of these fine 30 papers that are on the archive now, maybe 27 so far, but soon 30. We're also looking at higher order statistics and harmonic space and peak statistics. So you will see some of these papers appearing shortly. Marco Gatti, Penn postdoc, and I and our collaborators are looking at the third moment, which should be fun. Okay, so to conclude, I will spend 5 minutes returning to these tensions. So there's the CMB at age 400,000. There's our galaxy surveys at age 1 to 14 billion years. Does the standard model describe both of them? If you look at the power spectrum and translate all possible observables to it, it looks pretty good at the factor of 2 level. But what about the 2% level? That's the result I showed. The tension in our results is not strong. It's either 1 sigma for these black contours or 2.5 sigma at most for the lensing only result. So this was a bit of an anticlimax. I won't deny it, at least for many of us. We had a 2 sigma tension 3 years ago. We thought we are now analyzing 3 times as much data. Our error bars are going to get smaller. maybe it'll become a 3 sigma tension. Instead, it became less significant. So the contours got smaller, but they shifted a little towards the CMB. So we are still left hanging. If you're really interested in the future, much better data sets like LSST and Euclid, that's intriguing. If you're a theorist who was waiting to get like a big puzzle to play with, you might be disappointed. But that's life. The universe doesn't always cooperate with our hopes. To give you a flavor for other results, this is just the strongest, one of the strongest statements of the tension from the kids survey, which tends to get lower S8s and sigma 8s. So here they've combined their data with redshift space distortion results from BOSS and 2DF lens, and they get up to 3 sigma tension from Planck. This was published last year, so it has an older result. So it's still true that we have an H0 tension and a sigma 8 tension. The universe is expanding faster and has smaller fluctuations than expected. These are the numbers from a slide by a Penn postdoc, Tanvi Karwal, that the H0 tension, if you use the Shoes H0, is more than 4 sigma, but there are other results that are like 2 point some sigma. The S8 tension is also 2 sigma. So I may have talked about some of these theory stuff earlier, but how do we resolve these tensions? Theorists have mostly focused on the H0 one by introducing new species or interactions in the early universe, messing with gravity. A particular model that's been studied a lot is called early dark energy. So there was inflation. There's the accelerating universe today. Early dark energy is like a 3rd episode where dark energy showed up at the 10% level, and it changed the sound horizon such that the H0 tension gets partially resolved. We are hoping to put out a paper shortly where, with my theory colleagues at Penn, we are looking at couplings of dark energy to matter. Jeremy Saxton and Mark Troughton have looked at couplings to neutrinos, both of which rely on a possibly interesting coincidence that this episode of dark energy is coincident, roughly speaking, with matter radiation equality and with the energy scale of neutrinos, which happens to be about recombination. So anyway, these are, these early, exploratory, theoretical explorations, which involve some kind of fine tuning or additional ingredient to try to go beyond lambda CDM and explain all the data. We also came up with a counterexample a couple of years ago to the prevailing wisdom that the new physics has to be in the early universe. There's a very good reason why people concluded that the new physics has to be pre-recombination. And the reason, in one word, is the supernovae data. The supernovae data extends from present day to redshift 1.5 or so. And so you're really tightly constrained in what you can do to the late time universe, because any change to the mass density over this redshift range gets ruled out by the supernovae data. But we showed that there's subtle physics between Cepheid calibration and supernovae that can let you change the estimated H0 locally. People are starting to tackle both the H0 and sigma 8 tensions. So this slide is from a couple of years ago by Francis Yancey Racine, where generally speaking, you find that if you come up with a theory to address the H naught tension, which requires moving in this direction, you worsen the S8 tension, which wants this arrow to point this way, but most theories end up pointing the wrong way. So whether this is close to a theorem or just the limitation of models that have been tried so far remains to be seen. Meanwhile, we are also pushing ahead with, more model-independent approaches. So graduate student Minsu Park led this paper we did on reconstructing dark energy, which some of you at IUCA have looked at in the past. And we found that if you start with a quintessence model, in which you don't allow W to go below -1, then when you reconstruct W, this is redshift 0 to 1.5, using all the data, then if you toss in the H naught tension, you're really squeezed to lambda CDM. But otherwise, you're still pretty consistent with lambda CDM with some room to play. And so we had some comments on this swampland conjecture, which is kind of a fun new twist that string theorists have given us, finding some possibility that, it may be in trouble with new data. So I'll wrap up here. I'm sorry I couldn't give you a lot of the interesting details of the story, but the bottom line is that we fit lambda CDM, we have 2 puzzles, most of the measurements of the late universe support this puzzle. I didn't show you all the different estimates of sigma 8 and H naught. There's some disagreements, but they're mostly all supporting these puzzles. And so there's theoretical work and of course, plenty of observational work ahead. Because I only showed you results from 2-point statistics, there's all kinds of additional cross correlations, higher order statistics, and the scary and possibly powerful approach of just doing complete machine learning that is starting to mature. So the idea is that you make that kappa map that I showed you, you simulate every model, you inject all the systematic sources of uncertainty in the model, you train a deep learning network with it, and then you throw the data at it, and the network tells you which is the right model. So this kind of scary fantasy is actually happening. So you've heard many caveats about how artificial intelligence is creeping into our lives. Even in cosmology, it's happening. And so I'm actually discussing with some of these practitioners about whether we can play the role of a third-party broker to validate their methodology, but that could be a lot of fun as well. So I'll stop there. Thank you very much.
Thanks very much, Bhunesh. That was fantastic. Wonderful talk. I was also amazed that at the peak today, we had about almost 100 people on an unusual time. And that's, I'm sure, attracted by the glamour of the speaker and the topic. And just, I hope there'll be lots of questions. Please use the reactions button on the down, and then you have a hand up. Please put your hands up if you have a question, and I'll unmute you for your question. As we wait for the hands to come up, Bhunesh, let me use my privilege of having the button here to ask you. So if you're looking forward, as you said, to Euclid and LSST, Ruben, to say, what parameter do you think, standing now, what parameter do you think is going to be most illuminated in the first year or two after, say, Euclid starts publishing results?
So that's a great question. I mean, one of the exciting things about Euclid and LSST is that they will go beyond these 2 parameters, sigma 8 and omega matter. And there's different ways to do that. So there's no unique answer to that, but you could imagine, measuring W in redshift bins. Right now we are estimating an effective W. So you and some of your colleagues have looked at this, most interestingly, actually, how to do principal components of W. You can, of course, measure it in different Redshift bins, but you can also do principal components to get at 2 or 3 parameters for W. You can also just completely shift gears and measure the growth of structures. So separate geometry and growth and look, and to the extent that geometry is probed better by BAO and supernovae, you can look at growth, which is the unique thing that these galaxy surveys tell us about, and see if there's any tensions in the growth parameters themselves.
That is because you have a wider redshift distribution of these sources, I mean, to which you're measuring distances, compared to what you have in DES, which you haven't gone that far.
Subaru HSC survey gives us a preview of that. The lever arm is much bigger, but LSST will, of course, combine, area coverage with depth.
Great, thanks. We have Shuchetana Chatterjee's hand up. Shuchetana, go ahead. Yes, go
ahead.
Okay,
thanks. Great talk, Bhuvnesh. So I was just curious if it makes sense or not. So can we do, so if we look at the shear field of DS, the mass map that you showed, is it possible to do like a ISW kind of analysis to have some handle on the dark energy equation of state, or just understanding dark energy itself? Like cross-correlating with the CMB maps, the mass map from DES and CMB?
Yes, the cross-correlations with CMB are very powerful. And we have, a set of papers that should be out by the end of summer or early fall on that. The main cross-correlation is the DES galaxies with the CMB lensing.
Okay.
Lensing of the CMB. That has a pretty rich information. There's also the Sunyaev-Zeldovich effect, which of course is more of interest for the hot gas, but also as cosmology. And the ISW is really actually requires full sky and more redshift. And it doesn't need the kind of dense sampling of galaxies that we have. So surveys like DES or even LSST that's not their strength.
Okay.
ISW effect has already been measured using quasars or radio sources that span a wider range of redshift.
Okay, thank you.
Thanks very much. Thanks, Shuchetana. Next question is Surud has his hand up. Surud, go ahead.
Yeah, hi Bhuvnesh. Thanks for summarizing these DES results. So my question is a little bit about this red magic sample. I know that you guys are working on this, and so it may be a little bit premature to ask this question, but in DES year 1 data, of course, the red magic sample was the fiducial sample for the analysis. So did something change in between, like year 1 and year 3 in the scheme in which the sample was constructed, or have you tested, like, for example, if you take just the red magic sample, but only that you have right now, but then constrain it to the year 1 area, whether you still see these tensions or not?
Yes, there are a lot of these tests that we've done, including what you just described. And we haven't nailed it. There are a lot of clues, and we'd love to discuss with you. There are many things that we can discuss. Showing results that we haven't been able to include in our papers yet. But the short version is that yes, the sample selection changed, but the main thing that we think happened is that the depth uniformity of the survey, the year 3 is actually at a weak point in that uniformity, because the survey was designed as a 6-year survey. So that data set will have greater depth and greater uniformity. Year 1 actually had a smaller area and more uniformity. Year 3, we decided to go for the full area, but don't have as much uniformity. So we think that's responsible, and we think galaxy clustering is what's affected, but we don't have the complete proof yet.
Yeah, interesting. I mean, yeah, it is quite difficult of one to get, and there are all sorts of deep projections that you are trying to do, right? But it may not be entirely removing the issue. So, another question, if I may ask, it's more a philosophical thing, right? I mean, you had to do or drop a few samples after unblinding the data set. So, how did you actually approach this particular issue? And so, for example, if you use all the Maglev bin samples, which is now your fiduciary, right? You still had to drop out 2 of the last Redshift bins, right? So how much shift does that cause? And were there like musings about how exactly to do this, and whether there is a better way or a particular way, right, in which you can do these analyses post-unblinding? Because it's just something to learn for HSC as well, right? So
yeah, absolutely. I mean, chances are whatever problems you have will be different. But yes, we agonized over these things enormously. And it's certainly, not an ideal situation. There was a huge debate and a sentiment towards just publishing what we had in November is when we unblinded. But we thought it was, because we had 2 samples, it was worth looking at the other sample. And then for the Maglev sample, bins 5 and 6, A, didn't carry a lot of information, and B, were clearly a bad fit to lambda CDM. So to the extent that you can raise our primary goal as doing an exercise within lambda CDM and testing consistency with CMB, you have some objective justification for dropping those bins. But for other purposes, it's less comfortable to drop subsets of your data after unblinding. But because we thought that maybe a similar issue is affecting those high Z bins, we dropped them. On the other hand, you can see in our papers that doing the full 3x2 cosmology with red magic or with all 6 bins of Maglev produces a very small shift. So at the end of the day, we did take a lot of reassurance from the fact that this multi-pronged approach of having both lensing and galaxy clustering and significant redundancy leaves you with a result that was robust even to this significant systematic. Of course, another thing that we pursued is, what if it's not a systematic? And what if it's related to this lensing is low issue? And what if the potentials are unequal because it's modified gravity and clustering and lensing respond differently? And we are pretty confident that's not the explanation, but I wouldn't discourage people from looking into it more closely.
Yeah, thanks, Bhunesh.
Thanks very
I'll
much.
talk more, of course, later on.
Yeah. Your sigma 8 is still very low, right? Kandu next, Kandu.
Yeah, interesting, Bhunesh, the talk, because you emphasize more all the difficulties than just selling the results. I had the following question. You had this whole range of redshifts. So did you also get some information on the growth of fluctuations? I mean, you are showing all S8, sigma 8, all these things at present day, I thought. But so is it all consistent with lambda CDM, or what was this statement there?
Yes, if you use all the redshift information and look at the tomography, and one way to do that is to look at the overlay of the measurements of different redshifts with the best fit model, it's entirely consistent with lambda CDM. But we do have follow-up papers in which we look at that more directly, like growth of structure versus redshift.
Okay, thanks, thank you.
Thank you. We have Indulekha's hand up. If you're up to more questions, Bhunesh, I'm unmuting Indulekha. Go ahead, Indulekha.
It's more a doubt than a question. If the dwarf galaxy problem is actually real, in the sense the paucity of dwarf galaxies is real, that mismatch between simulation and observation, which way does it go as far as these results are concerned?
So I think you're referring to a problem of cold dark matter about the abundance of dwarf galaxies and the related problem about the core versus cusp of galaxy profiles. Those question the nature of dark matter, which doesn't directly play with the results that I showed, which are on much larger scales. And my understanding of that story is that there are many ways you can question and doubt cold dark matter, but that the dwarf galaxies are not considered a compelling problem. I think mainly because of theoretical advances, but possibly also measurements.
Thank you.
Thanks, Bhunesh. I hope you can take a couple more questions. You do have a throat problem, I can see. But
I also have to take my daughter to school, but I'll take a couple more questions.
Two quick questions. One is from Varun Sahani, who has put it in the chat box for me to read out because he can't connect right now. He says, I've been reading your excellent review with Justin Curry on modified gravity. As you know, weak lensing is a means to test MOG models, modified gravity models, since it's sensitive to both gravitational potentials phi and psi. Can you say something about constraints on this from DS?
Again, this will hopefully appear in a follow-up paper, but as you can see from the results, to the extent that we are consistent with lambda CDM, there is no signature of a breakdown of phi equals psi in the data at first glance. Yeah.
Right. So we look forward to that. That'd be very, very interesting. Okay, last question. Sharbari has her hand up. Let's see if it's a quick question because Bhunesh has to go. Sharbari, go ahead. I'm unmuting you.
Hi. Yeah, it's a really brief question. You mentioned at the beginning of your talk that your DES has some results or some new discoveries in the outer solar system. So if you could just quickly comment on that. Just a curiosity. Thank you.
Because we're observing for the 6-year period with like a 1 minute, a 2 minute cadence, you can look for moving objects. So my colleagues in DS, Gary Bernstein and Dave Gerdes, and the students, Pedro Bernardinelli in particular, have discovered a bunch of trans-Neptunian objects, Kuiper belt objects, and address this question of, is there any evidence for the gravitational influence of a planet 9 on these objects? That's a very difficult question to answer, but at least so far, there's no evidence for it.
Okay, thanks. Yeah, thank you.
Great, thanks very much, Bhunesh. It was a fantastic evening. I know you have to go. So on behalf of everybody, applause on Zoom. Thank you very much.
It was a real pleasure.
Thank you very much.
You're welcome. My pleasure.
Thanks, Bhuv. I will send you an email separately then.
Sounds great.
More questions. Yeah. See you.
Bye-bye.
Just for those who are still left in the audience.
Oh, yeah, that's right. You had an announcement to make. Quick.
Yes, on Thursday, there is a colloquium by Tommaso Belloni at the usual time of 4 o'clock. We have been having some difficulties with our mailing, and even if you don't get the mail, be there at 4 o'clock if you are interested in this colloquium. And yeah, thanks.
Sorry, I forgot to ask you.
No problem, Shoma. Yeah.
But we'll have to find out a way of sorting out this mailing problem.
Yes.
Why is
Thanks,
this?
everyone.
Thank you. So what is this issue? The people who forward to Gmail are not getting their mails? Is that what you're saying?
Yeah, I think Gmail blocked